Okay, for this example, we have data on the age distribution of jurors in a jury sample. So the idea of a jury is that you have a representative sample from the public, and so our expected values are going to be the number of jurors that we would expect in each age group. So here we have the age groups. So 20 to 40, 21 to 40, 41 to 50, 51 to 60, and then 60 plus. And these are the county-wide percentages. So 42% of the county is in the age group 21 to 40. Now for the numbers of jurors that we have 5 in this age group, 9 in this age group, and so on. So this is our observed totals. If there was a representative sample from the public, the percentage in each of these categories would match this. So now we need to calculate what the expected values are. And so this is an additional step if you're comparing this to, say, a t-test. In a t-test, you're looking at two different groups, and you have the mean of each group. And then to do the t-test, you basically, in Excel, you highlight each group's data, and then that's it, right? It gives you a p-value. To do a chi-square test, which is what we need to do here, and in this case, it's called a goodness of fit test. How well does the actual distribution of data fit the expectation? What we need to do here is figure out what the expected values are. So that's an additional step that you have to do when you run chi-square tests. You have to figure out what the expected values are that you're comparing to. So here's the observed data again, 5, 9, 19, 33. And these are those county-wide percentages. So this is the table that we just saw. And then we've added in here what are the expected values. Now we get these expected values because we know the percentage that they should be. And we also know the total number of jurors that you have. So we have 66 total jurors. 42% of them should be in this age range to match expectations. So 42% of 66 gives me the 27.72. And so we do that for each of the different age ranges using the 66 total jurors. And this is what we would expect in each category if the jury sample was representative of the population. All right. So now that we have this information, observed and expected, we can run the chi-squared analysis. So if you're working in Excel, you can get the answer most quickly using this function here. So the equals chi-square, CHISQ, dot test, and then you highlight the observed data and the expected data. So let's do that first, and then I'll come back to the other things like calculating this quantity and degrees of freedom. Because we have the observed and the expected values, we can come over here into Excel, the same data, observed and expected, and I've calculated from the chi-square test what the p-value should be. And so what did I do to get that? Well, let me just start again. Equals chi-sq dot test. And then we're putting in the, Excel calls it the actual range, but we've been calling it the observed data. So the actual range is this set of values. So I'm highlighting that. Note that I didn't highlight the total. I just highlighted the observed total in each category. And then comma, the expected. So I highlight the expected range. And that's it. So very similar to when you're running a t-dot test in Excel, you'd highlight one group of values, then the other group of values, and it would spit out a p-value. When I do this, it'll also spit out a p-value for the chi-square test. And it tells me that it's 3.15 whatever times 10. So E means times 10 to the power of minus 13. So that's basically 0. So there's almost 0 probability that this distribution would be observed if the expected values were true, right? In other words, if the jury was selected at random from the population, there's no chance that you would get this distribution of data. So we can reject the null hypothesis. Okay, so that, in essence, that's all you have to do. You have the observed, you have the expected, you can run the chi-square test. But to get a little more insight into actually what's happening, we can go through the calculation kind of step by step so you can see what this is actually doing. Now, the chi-square test is based on a parameter called chi-squared. And that chi-squared is calculated. If we come back to the PowerPoint here for a second, let's see, where do we define chi-squared? Right here. So we define chi-squared as the sum of observed minus expected squared divided by expected. Okay, so we need each of these values subtracted from each of these values, square them, divide by the expected, and then add them all up for each category. So in this column here, that's what I've done. This number is observed minus expected squared divided by expected. So you get 18.6. You add them all up, and the total here, that's your chi-squared value. So chi-squared for this data set is 61.3. Okay, so that's where this 61.3 comes from. Then the chi-square distribution function in Excel, chi-square.dist, will tell you the left tail probability for this chi-squared value. And so let me delete this here and we'll calculate it again. The chi-square dist function, chi-sq.dist, wants the value. It calls it x, but it's really the chi-squared value, so I'd click that. Then the degrees of freedom. And so if you remember, degrees of freedom is the number of different categories minus 1. And so there's 4 categories. So our degrees of freedom in this case is 3. And we want the cumulative distribution function in this case. So we're going to say true. And so that's the value that was here before. It's 1.000. That's the left tail probability. So the probability of getting a chi-square less than 61.3 is essentially 1, meaning 100%. The right tail probability, which is what we call the p-value, the area in that tail, is 1 minus this value, right, which is going to give us 0, of course. And that's what this is essentially. This is telling us 0 as well. So these two are in agreement with one another. They're giving us the exact same information. It's giving us the p-value for this chi-squared, running a chi-squared test on observed and expected values from the table. So what we find is that there's no probability that this jury sample could have come from a random sample of the population. Thus, the null hypothesis would be rejected.